The Amazing Eratosthenes. Let's take a fun trip back to ancient Egypt and find out why this guy was so amazing. Eratosthenes was a Greek scientist working in ancient Egypt for the pharaoh. He is most famous for his amazingly accurate estimate of the size of the earth in a brilliant experiment that he conducted at the dawn of recorded history in 240 BC. In this video, we'll take a hands-on approach and see how he accomplished this seemingly impossible task. To begin, let's warp back to 2560 BC. When the ancient Egyptians built the Great Pyramid of Giza. Even that far back, the Egyptians were able to align the largest pyramid ever built to better than 1/10 degree accuracy to true north. The ancient Egyptian builders and surveyors were no slouches in producing amazingly accurate measurements using the crudest of tools made of wood, string, stone, clay, and other available materials. In 332 BC, Alexander the Great conquered Egypt and installed his own dynasty of pharaohs, the so-called Ptolemies. Around 240 BC, Eratosthenes lived and produced his famous estimate of the Earth's size, the earliest known based on scientific methods. If you notice in that picture of a Ptolemy pharaoh, there are pyramids in the background. On the table is a globe, indicating that the Greek and Egyptian scientists already realized the Earth was a sphere. In 1492, Christopher Columbus stumbled into the New World, using an estimate of the size of the Earth far smaller than Eratosthenes. In the 1732 years between Eratosthenes and Columbus, no one had actually sailed around the Earth, so the size estimate was subject to a great range of values and methodologies. Around 245 BC, Pharaoh Ptolemy III hired Eratosthenes as tutor for his kids and as a librarian at the Great Library of Alexandria. Egypt is a hot, dry, desert country, pretty much, and the Egyptians were vitally dependent upon the Nile River for fresh water, irrigation, fishing, and transportation. Most of the people lived in a fertile strip along the Nile and in the fan-shaped Nile Delta. Once a year the Nile would flood, carrying silt from the south, which would fertilize the farmlands. Sometimes the floods would not come, causing drought and starvation in Egypt as the crops failed. The Egyptians always lived in a precarious balance with the Nile, at least until the Aswan High Dam, built in 1970. Sometimes heavy floods would overwhelm the banks, washing out roads, villages, farmlands, and livestock. The farmers needed to know the cycles of the Nile and the seasons, when to plant and harvest, when to expect floods, and when the seasons would change. Predicting these events accurately was vital for the farmers, but also important for the pharaoh to support taxation. This gave rise to Egyptian surveyors, recorders, early science, and bureaucracy. When the Nile flooded, it often washed away land markers, and the surveyors had to reestablish these markers to avoid fights between landowners. Predicting seasons was key to agriculture, and the Egyptians knew the seasons were linked to the periodic motion of the sun and stars. The ancient Egyptians recorded data on the sun and stars and used this to predict Nile floods and weather cycles. Their motion was so important that it got incorporated into the religion. The sun would be born in the east right across the sky and die in the west each day. Stars were known to rotate around a north star, and finding local true north was easy in a mostly cloudless sky. Even children in ancient Egypt were aware of the cycles of the sun and could play games by tracking the shadow of an obelisk with rocks during the day and throughout the year. By plotting the tracks of these rocks, they could come up with the motion of the sun during the shortest and longest day of the year. High noon occurred when the shadow was the shortest, and the length of the noon shadow varied throughout the year between limits, which marked the summer, June 21st, and the winter peaks. As chief librarian, Eratosthenes would have had access to the historical archives of Egypt from ancient times. Legend has it that he noticed one report from the residents of Aswan which stated that there was a deep well there with an interesting history. Every year on June 21st at high noon exactly, the overhead sun shines directly down the well, casting no shadow. At no other time of the year did this happen. And there's noon. This report caught his immediate interest. He was already convinced the earth was a sphere, so this event in Aswan meant that at high noon he could draw a straight line between the sun, the well, and the center of the earth itself. He checked the sun records for Alexandria, a town 524 miles north of Aswan. Sun trackers in Alexandria reported that stone columns there cast a noticeable shadow at noon on June 21st. And there's noon. He started thinking about why this difference and what might cause it. Notice on this model there are three pairs of obelisks, one on a flat white plane, a slightly curved blue surface, and a more curved red surface. Notice that the shadows on the flat surface stay equal during the sun's motion. But when the sun is directly overhead, the curved surfaces show one with no shadow, while the other casts a shadow. Also, the greater the curvature, the longer the noon shadow. So in Eratosthenes' mind, the Aswan and Alexandria shadow situation was telling him something about the curvature of the earth itself. This was a key clue for Eratosthenes, and he started drawing models with the sun, the well, and the earth to see what's up with that. He put together the following model, which is key to understanding his famous experiment. The model makes four key assumptions. First, the sun's rays at Aswan and Alexandria are parallel. The earth is a sphere. Alexandria was directly north of Aswan, that is, local noon occurs at the same time. Lastly, line segment AC transverses the two parallel rays. Let's look at these assumptions. Why did Eratosthenes assume sunlight struck the earth as parallel rays? Well, from vertical columns it was easy to observe how the shadows moved during the day, showing the sun's rays were parallel as they struck the earth. From Euclid he knew that if the sun and earth were very distant, the incoming rays would be so close to exactly parallel that he could ignore any small errors, simplifying the problem. Why did Eratosthenes assume Earth was a round ball, a sphere? The port city of Alexandria was founded in 332 BC by Alexander the Great to expand and regulate trade between Egypt and the Mediterranean region. He constructed a complex of harbors and canals to link maritime shipping with the Nile and inland waterways of Egypt. The Pharos Island lighthouse was built at the entrance to Alexandria Harbor. The lighthouse kept a fire burning 24/7, which could be seen at night many miles. During the day, the smoke column could also be seen by ships and help guide them safely to port. When Eratosthenes watched ships departing, he observed them slowly sink out of sight over the horizon. When he climbed the lighthouse, over 400 feet high, he could again see the ship. This was certainly more consistent with a round Earth than a flat Earth. The next evidence came from watching the stars from the observatory at the library. He was famous for mapping over 700 stars, and by plotting the motion of the stars, he could easily trace them wheeling around a central point. At night, it was easy to find the direction to true north by finding the one star which appeared stationary through the night. Thuban in those days. To Eratosthenes, this circular motion clearly rotated around an axis running through the top of the Earth, or true north. Either the Earth was a ball which rotated every 24 hours, or the Earth was fixed and the heavenly shell rotated every 24 hours. Which do you think he thought it was? Lastly, the sun and moon were spheres. Some planets appeared as tiny balls, and lunar eclipses showed the Earth's shadow across the moon as circular. Eratosthenes would have made the connection to the midday sun event moving across Egypt from east to west and to the same 24-hour rotation of the stars at night. Towns along a north-south line, a meridian, would experience high noon simultaneously as the meridian line swept east to west every 24 hours. Why did Eratosthenes assume Alexandria was directly north of Aswan and that local noon would occur at the same time in both locations? There are many possibilities, but some likely explanations. Local north was easy to establish by the sun-shadow method or by sighting the North Star at night. This also set the other local cardinal points, north, south, east, west, and bearings in between. The local surveyors would have identified and mapped stationary reference points, such as prominent land features, obelisks, wells, etc. The local data would be used to build larger section maps until the whole of Egypt was mapped. Also, good maps were critical to the pharaoh. They fostered better land and sea navigation, fewer wrecks, lost caravans, etc. They settled land disputes after Nile floods. They helped maintain roads, waterways, and trade routes. They facilitated taxation and land concessions. And military uses. There's the famous lost army of Persian King Cambyses II. 50,000 warriors were lost in a legendary sandstorm in 525 BC. So the pharaoh had powerful reasons to invest in good surveyors, maps, and scientific experts to support key government function. Why did Eratosthenes assume line segment AC crossed or transversed the two parallel lines formed by the sun's rays? Living just before Eratosthenes was Euclid, another Greek famous as the father of geometry. Euclid's Elements of Geometry had shown that lines cutting across parallel lines, transversals, have special properties. The best way to see it is to take it step by step. He showed that if the yellow lines are parallel, then the red transversal would cut across both yellow lines at the same angle. On the figure, angles S show this property. These angles are called corresponding angles, and Euclid showed they are always equal if the yellow lines are parallel. That is intuitive looking at the figure, but Euclid proved it. The next property was when two lines crossed, they produced equal angles across the vertex. These are called opposite angles, and Euclid proved they are equal. Lastly, since all three angles S are equal, the bottom angle S equals the middle angle S. These are called alternate interior angles, and Euclid proved they were equal for any line traversing parallel lines. So, using basic geometry, Eratosthenes drew the simplified Aswan-Alexandria model as shown. Angle S was the shadow cast by the obelisk in Alexandria. But more important, angle S was also the interior angle from the center of the earth to both cities. This was his great insight. If he could somehow measure the angle of the shadow at Alexandria on June 21st at high noon, he knew that at Aswan there was no shadow there at that moment. It greatly simplified things. The other thing he noticed, remember the earlier picture that showed the greater the curvature, the longer the shadow? Somehow the angle S was saying something about the curvature of the whole Earth. Then he realized that if you know the distance over the Earth between Aswan and Alexandria, now known to be 524 miles, you could use a pizza slice approach to overlay slices until the entire Earth was covered. However many slices of equal size it would take to fill the pizza would allow multiples of the distance between the two cities to be added until the whole Earth was spanned. This simplified model would potentially allow Eratosthenes to measure the entire Earth. He only had to know the distance between two cities and the angle of the shadow at noon on June 21st in Alexandria. Not bad for 240 BC. We're almost there. But how did Eratosthenes in 240 BC measure the angle of the shadow in Alexandria? Firstly, he would have probably used a tall vertical structure with a pointed top, because it would have cast a longer shadow with an unambiguous apex. He may have used a gnomon or tall thin obelisk, but nobody knows for sure. He might have purpose-built and calibrated an instrument as precisely as possible using Euclidean geometry. Egyptian pyramid builders had already developed methods to get a perfectly flat base and plumb obelisks to the vertical most precisely. All that was missing was calibration. He knew from Euclid it was easy to bisect any angle using nothing more than a straight edge string and a mark. The red circle is drawn centered at the vertex, and green circles are drawn centered where the red circle intersects the line. Radii R are drawn from the centers of the green circles to where they intersect. Finally, the line connecting the center of the red circle and the intersection forms two identical triangles, back to back. Since corresponding angles of these triangles are equal, they split the angle A into two equal subangles. Eratosthenes could have used this simple method to keep bisecting angles to smaller and smaller fractions of a full circle, producing 1/2, 1/4, 1/8, 1/16, and so on, as far as materials and eyesight allowed. He could have produced a shadow scale similar to this to measure the shadow angle, or some variant of it. The details of the equipment Eratosthenes used are lost to history, but just for fun, let's do our own experiment using a tall pointy obelisk casting shadows onto circles on the ground marked in degrees. Eratosthenes did not have the degree system for angles. He would have used Egyptian units. But just for fun, let's do our own experiment using modern degrees and miles. So here we are outside the Great Library of Alexandria on June 21st in the year 240 BC. The Aswan well is shown in the lower right to compare both locations. Let's fly above the obelisk and the well so we can look straight down. We're waiting for the sun to come up. So here we go. Here comes the sun at noon, then sundown. Did you catch that? Well, Eratosthenes did not have instant replay, but fortunately we do. In his experiment, he would have captured the moment when the shadow was shortest, marking local high noon. As you can see, the well in Aswan cast no noticeable shadow, but in Alexandria, there is a noon shadow. The shadow angle is a little more than 7 degrees. I read that as 7.2 degrees. Eratosthenes reported his results in terms of fractions of a full circle, reporting that the shadow angle was 1/50th of a full circle. A full circle being 360 degrees divided by 50 equals 7.2 degrees. Eratosthenes now knew that the angle S in our previous previous drawing was 1/50th of a full circle. As a side note, here's what he would have seen if he had used his simple angle scale, showing the shadow angle as approximately 1/50th of a full circle. Now let's see what Eratosthenes did with this information. Using Euclid's proof that alternate interior angles of a transversal across parallel lines are equal, he then knew that the central angle between Alexandria and Aswan was 1/50th of a full circle, and that the distance was 524 miles between the two cities. Eratosthenes would have reasoned that if one pizza slice of angle 1/50th was 524 miles along the outer edge, then two pizza slices fitted together would have a total central angle of 2/50ths of a full circle, and the distance would be doubled to 1048 miles. So using this method, he would have multiplied the 524 miles by 50 to estimate the distance around the entire Earth. That equals 26,200 miles. The current value is 24,860 miles. Eratosthenes did this estimate in 240 BC, more than 22 centuries ago, using little more than string, obelisks, wood, stone, and a few camels. He also had the great records, tools, and tradecraft of the Egyptian surveyors and pyramid builders that came before. An amazing accomplishment by any standard. Eratosthenes did not have modern units of distance. The Egyptian unit was the stadia, and it is not known which value for the stadia he used. Some references say the stadia was 500 feet, others 600 feet, etc. Eratosthenes reported the distance between Aswan and Alexandria was 5,000 stadia. Some legends say he used the time it took a camel to walk between the two cities to estimate the distance, but nobody knows for sure. It is likely the Egyptian surveyors mapped the country more accurately over the centuries, but it's also possible that as chief librarian, he may have commissioned a special survey to confirm the maps. But in any case, this table compares some common values to bound how close he came in 240 BC. No matter how you slice it, we're talking 240 BC, using the crudest of tools, techniques, and tradecraft. We hope you enjoyed this video as much as we enjoyed making it. If so, please feel free to share with your friends and teachers. We would love to hear your feedback, so either click on one of the rating icons or better yet, leave a comment. We are grateful to the thousands of viewers, young and old, who watched this video and this amazing story of early science in ancient Egypt. After learning about Eratosthenes' famous estimate, we came away with renewed respect for our ancient elders and the power of observation and scientific reasoning. Clearly, technology has changed greatly, but human ingenuity has not so much. We truly stand on the shoulders of giants. It is especially rewarding to know that kids in every country of the world have watched this video. Your many kind comments have certainly justified our efforts to share this amazing story with you all. To as many of you as possible, and with apologies for any injury we may do to your native tongue, we say, Shukran, Safraisto, Domo arigato gozaimasu, Grania mate, Dziękuję bardzo, Grazie, Sheshe, Tanyavad, Spasiba, Mamnunum, Obrigado, Gracias, Merci beaucoup, Tak, Asante, and finally, thanks from Lily Bean Productions. If you enjoyed this mixture of science and ancient history, you might also enjoy our Amazon ebook, Christopher Columbus and the Land Bridge. This is colorful history and science for young minds. It weaves together epic tales, high adventures, and discoveries which set off world-shaking events. The basic story is simple enough to engage inquisitive youngsters, yet is meaty and salty enough to hold the interest of even jaded high schoolers. The book is based on a series of stories told to a kindergartner who became fascinated with the tales of young Christopher Columbus and kept asking, what happened next? It took a full year to complete the epic story through many enjoyable sessions. Since other kids probably have the same questions, we captured that memorable year of linked stories in this ebook. It got good reviews from young and old, including a modern mariner who said even they learned new details about ships and seafaring in the age of sail. The chapters bridge across the centuries to illuminate why the world shook in ways that no one could have foreseen, not just what happened. This is a good book to give to a young relative and a perfect book for reading to inquisitive kids.